Welcome to this explainer. Today, we're diving straight into explaining the chapter by decoding the secret mathematical language that models our everyday reality. You know, math isn't just numbers floating around on a page. No, it's the hidden framework behind how literally everything grows, shrinks, and changes over time. And today, we're focusing on one specific, absolutely crucial tool from that framework, the linear polynomial. Okay, let's dive right into this. Our roadmap today will take us from basic algebra grammar straight through to visualizing math in motion. We'll cover 1. The language of algebra. 2. What is a polynomial? 3. The input-output machine. 4. Modeling growth and decay. And finally, 5. Visualizing the line. Let's kick things off with section 1, the language of algebra. Because before we can build our mathematical machine, we really need to understand our raw materials. To anchor this in reality, let's look at a scenario directly from our source chapter. Imagine a guy named Raju going to a shop. The shop owner tells him, hey, these red sealed boxes always contain exactly 4 pens each, and the blue ones, they have exactly 5 pencils each. Now let's say Raju decides to buy some boxes, but we don't know exactly how many. He buys a certain number, let's just call it X, of red boxes, and a certain number, we'll call it Y, of blue boxes. And as a bonus, the shopkeeper throws in 3 extra pens for free. Nice, right? So how do we quickly figure out the total quantity of items he has? Well, if he has X red boxes, he has 4 times X pens. If he has Y blue boxes, he has 5 times Y pencils. Add in those 3 free ones, and boom, we get our algebraic expression, 4X plus 5Y plus 3. Now, let's translate those fancy academic terms into plain English using that exact expression we just built, 4X plus 5Y plus 3. First up, we have our variables. These are the unknown letter numbers like X and Y. They represent the quantities that can change. You know, in Raju's case, the actual number of boxes he decides to buy. Next, we have our coefficients. These are the fixed numbers explicitly attached to our variables, like the 4 and the 5. They basically tell us how much of something is inside each variable unit, like those 4 pens per box. And finally, we have our constants. This is a fixed number standing all on its own, like the 3 extra free pens. It doesn't change no matter how many boxes Raju actually walks out with. All right, moving right along to section 2. What is a polynomial? Now that we know the basic words, it's time to learn how math categorizes these expressions based on their power. See, algebraic expressions involving variables and their powers are called polynomials, and this brilliantly illustrates how neatly we can organize these equations based on what we call their degree. The degree is simply the highest power of the variable present in the expression. Let's look at the table. If the highest power is 3, like in the example 5y cubed plus y squared plus 2y minus 1, we call the whole shebang a cubic polynomial. If the highest power is 2, like x squared plus 5x plus 1, well, we call it a quadratic polynomial. And if the highest power is just 1, like 3z plus 7, where that z effectively has an invisible 1 as its exponent, we call it a linear polynomial. But here is the absolutely most important thing to remember for today's explainer. We really only care about polynomials to the degree of 1, the mighty linear polynomial. That number 1 is our main focus, because equations with a degree of 1 possess incredibly unique and predictable properties when we apply them to the real world. So let's see how that works in section 3, the input-output machine. A linear polynomial isn't just a static string of letters and numbers on a page. It's actually a dynamic working machine. Let's walk step by step through this substitution process using a simple linear polynomial, 2x plus 3. I want you to think of x as your raw material. Step 1. We input a value for our variable. Let's say we set x to equal 4. Step 2. We drop that raw material into our machine and apply the function. So we substitute 4 into the expression, giving us 2 times 4 plus 3. Step 3. The machine runs, does the arithmetic. 2 times 4 is 8, plus 3 gives us our finished product, an output of 11. Every single time you change the raw material, the input x, the machine gives you a corresponding finished product, the output y. Now let's take our machine out into the real world. Section 4, Modeling Growth and Decay. We're going to track how things actually change over time. Linear expressions are absolutely perfect for modeling situations where there is a constant rate of change. On one hand, we have linear growth. The chapter gives a great example of this. Imagine a village with an initial population of 750. Every single year, exactly 50 people move there from a nearby city. That constant addition of 50 people per year, that's linear growth. On the flip side, we have linear decay. Think of buying a brand new smartphone. The exact moment you buy it, it begins to depreciate. If its value drops by a fixed, steady amount every single month as time passes, that is linear decay. So linear addition models growth, while linear subtraction models decay. This brings us to our final pivot, Section 5, Visualizing the line. We're bringing the math into the visual realm by plotting our equations on a graph. When we graph these polynomials, they generally take the classic equation format, y equals ax plus b. Let's break down what those letters actually represent visually so you understand the lines before you even see them drawn out. The coefficient a is the slope. It literally defines the steepness of the line. If a is a large positive number, the line climbs steeply. If it's negative, the line falls, which visually represents that decay we just talked about. Then we have the constant b, which is the y-intercept. This simply marks the exact spot where our line cuts across the vertical y-axis. Now, what's really interesting about this slide is seeing this in action. On the left, we have a super simple graph, y equals 2x. Here, our y-intercept b is 0, so the line passes perfectly through the origin point of the graph. The slope is 2, so it rises steadily. But look at the graph on the right. Here we have a whole family of lines, y equals 2x plus 5, y equals 2x plus 1, and y equals 2x minus 1. Notice what they have in common? They all have the exact same slope, too. Because the steepness is identical, they create perfectly parallel lines. Changing the b value, that constant at the end, doesn't change the angle at all. It merely shifts the exact same line up and down the vertical axis. So the crucial point is summarized beautifully in this quote directly from the chapter. A linear relationship between two variables, x and y, is represented by a straight line, y equals ax plus b. That right there is the core takeaway of this entire explainer. This incredibly simple equation, with just a degree of 1, is the master key to drawing and understanding straight-line relationships. It represents a constant, predictable rate of change. To wrap things up, I want to leave you with a thought that connects this math directly back to your physical environment. Look around your room right now. What is experiencing linear decay at this very moment? If you're watching this on a laptop or a smartphone, take a quick glance at your battery indicator. Assuming it's not plugged in, that battery percentage dropping steadily over time, that's a perfect real-world example of linear decay happening right in your hands. Mathematics isn't just stuck in the textbook, it's everywhere. Thank you so much for joining me on this explainer, and keep an eye out for those linear relationships in your everyday life.